This is a little video about something called Dalton's law of partial pressure. Sounds fancy. It's a very simple concept. What it says is that if you have a mixture of a gas, the total pressure from that mixture will be the sum of the individual pressures of the gases that are in the mixture. Now I'm going to keep going for the sake of time. If you need to take time to write that down or something, just go ahead and pause the video. All right, so what that means is, like I'm sitting in a room right now, and just ignore this picture down here. I'm sitting in a room right now, and this room has oxygen and nitrogen molecules just flying around everywhere. I'm sitting right in the middle of them. They're all banging into me. If you're sitting in a room, they're banging into you too, but they're different molecules than are banging into me because we're doing, of course, our social distancing right now. Anyway, the 80% of the air in any room is nitrogen and 20% is oxygen. So I've set this up appropriately. I've got 4 molecules of oxygen and 16 molecules of nitrogen. So that's a proper ratio. Now, what the Dalton's law says is that the total pressure in the room, which is 1 atmosphere, is equal to the pressure of the nitrogen plus the pressure of the oxygen. So the total pressure is equal to the pressure of the nitrogen plus the pressure of the oxygen. Since 80% is nitrogen, then I know that 80% of 1 is due to the nitrogen, so that's 0.8 atmospheres. So we'd say 0.8 atmospheres plus 0.2 atmospheres equals 1 atmosphere. That's all there is to Dalton's law. It just says that the total pressure is the sum of the partial pressures. And if you're wondering how I got 0.8 again, it's 0.8 is 80% of the total. 0.2 is 20% of the total, which is 1 in this case because I'm sitting in a normal atmospheric pressure. All right, now where it becomes relevant in chemistry is when we collect a gas over water. So I should have done this before I started, but real quick. So we'll go to YouTube and we'll pull up a video of collecting a gas. Okay, collecting a gas over water. And here's a little animation that works pretty well. So if we heat this container of test tube potassium chlorate, you should know that it's going to decompose into potassium chloride plus oxygen. So that's just a normal chemical equation we've worked with before. As we start to heat it, eventually bubbles are going to come out. And when the bubbles, it melts first and then it starts to decompose. And see these bubbles coming out this tube? Well, there's water inside this cylinder, so the gas is pushing the water out. That's what we mean by collecting a gas over water. So the total pressure inside this little area right here is going to be exerted by the oxygen that we collected. Plus, when the oxygen goes through the water, it's going to make some water evaporate. So up here, you don't just have oxygen, you also have some water vapor. All right, so the total gas pressure that's up at the top would be equal to the sum of the oxygen molecules, which you see here, and the water vapor, which you see here. So if you add them together, you get the total pressure. So the P total equals the pressure of the oxygen plus the pressure of the water. Now, if you wanted to know what is the pressure of the oxygen, you would need to take the total pressure, which you could get experimentally. I mean, you just adjust the cylinder so that the water level inside the cylinder and the water level outside the cylinder are the same. Then you can assume that the pressure inside the cylinder, now when I say cylinder, you know what I'm talking about, it's this cylinder here. So you can assume that the pressure inside that cylinder was the same as the pressure outside. So you know the total pressure, and you know the pressure of the water because you can look it up on a table. And then you subtract that from the total, and it gives you the pressure of the oxygen. So the total pressure is the oxygen plus the water. To get the pressure of the oxygen, you subtract the water. That's all there is to how you handle water pressure calculations with Dalton's law of partial pressures. All right, now I put a link on the website right here to a water vapor pressure table. And it's kind of weird because it pops up like that, so you have to scroll down, but there's your table. So for example, right now the room you're sitting in probably has a temperature of about 22 degrees Celsius, and the pressure of water vapor would be about 19.8. Now let me go back to my pictures that I've been drawing. So I drew two flasks here. The two flasks both contain water and oxygen, and I put 4 water molecules in this flask and 2 water molecules in this flask. They're harder to see, but trust me, they're there. All right, so which flask has more area for the water to bang into? Well, the one on the left would have more surface area exposed to the gas. Now, there are more molecules in that surface area, but there's more area. Here, there's less molecules, there's less area. Okay, remember, pressure is force per unit of area. All right, so the ratio, like if you have 4 divided by 2 compared to 8 divided by 4 compared to 12 divided by 6, they're all equal to 2, aren't they? So as the force goes up, the area goes up, the ratio stays the same. All right, now one other thing, the water that's inside the flask evaporates, but it reaches a point where you can't get any more water molecules up here, so then it starts to condense. So you get something called equilibrium, where the process is going in both directions. Over here, the same thing happens, but equilibrium is established sooner on this side because there's less space up above the surface. All right, so again, what you're going to need to know how to do is find the pressure of the oxygen. To do that, you just subtract the water vapor pressure. And you go to this website, you're familiar with it, it's our homework site, and scroll down to this table, and that tells you what the water vapor pressure is. Okay, I think that's all we need to say about Dalton's law of partial pressures, and I'll post this one and move on to ideal gas laws and molecular weight.